Let's start. Thank you very much, Marielle Sáez, for accepting give a talk in our virtual meeting. Marielle Sáez works at the Pontifícia Universidade Católica de Chile, and she will talk about short-time existence for the network flow. Marielle, please.
Thank you very much for the invitation. This is for me also my first online conference. I've been to seminars, but this is the first conference. And well, I hope next time we'll be in Buenos Aires with a sal and everything. But for now, this is great. And it's good to see so many people that I know here and I haven't heard about for a while. Anyway, so the topic today will be short-time existence for the network flow. So I think the first thing is to introduce the topic. And I think when I was preparing the talk, I realized that it's somewhat long and it's hard for, I mean, this is the first time I'm giving a talk in this format, so please interrupt me if I'm going too fast or too slow. And yeah. The first thing that I'm gonna do is try to introduce what is the network flow, and I'm gonna start by talking about what is mean curvature flow. So mean curvature flow is the gradient flow associated to the area functional. That means the following. If you try to find critical points of the area functional, you would be looking for what are called minimal surfaces. And when you look at the parabolic version of that problem, that is mean curvature flow. And that translates then into a parabolic equation. I don't know if this is working. Yeah, that's working. That is the one that is written down there below. I'm gonna put a box here. Here, dt, you're thinking that x is a parametrization that depends on time. So this is deforming the surface in Rn plus 1. And you're deforming in the normal direction with speed h of x. And if you look at this equation, you see that I'm only prescribing how it's deformed in the normal direction, not in the tangential direction. And the reason for that is that the tangential direction, the tangential direction, let me go to the next slide. Well, this is what I said before. Critical points are minimal surfaces or geodesics if you're in one dimension. Okay, so this is the last point here that I wanted to mention. That normal direction that you see in the equation accounts for certain degeneracy that the equation has. That is the fact that you can always reparameterize and get the same surface. So there's a natural degeneracy embedded in this equation. And at the same, but despite of that, you can always get from that equation a quasi-linear parabolic equation. And what I wrote just above this is an example when you have something that is a graph. And locally, you can always think about a surface as a graph, or at least for a smooth surface, you can always think about it as a graph. And then the equation would look like this. So your coefficient, as you see, it depends on the derivative. And as long as you have bounded derivatives, then you're going to have a well-defined equation. But this may develop singularities in finite time. And that's one of the main things that you look at when you study actually mean curvature flow. But today I'm gonna focus in a very particular case, and I'm gonna start with, you know, in a even simpler case, that is the one-dimensional one. That is when you have curves on the plane. So everything is gonna be in Rn for now, although you can do this in any codimension and on any manifold that is regular enough, and on any Riemannian manifold that is regular enough. But I'm gonna focus today on curves on the plane, and more especially when everything that I'm gonna say more or less generalizes when you're codimension 1, so you can do this on surfaces as well, but higher codimension is quite different. So just think about curves on the plane, I would say. And then the equation, you have that what you're doing is deforming your curve in the normal direction with the speed of the curvature of the curve, and there's only one curvature, and that makes the problem a lot more regular and better understood in this situation. And when you're talking about regular curves, a lot is known in this situation. So I'm gonna just state two results here, two important results. And here I wanted to show you a video, but I'm not gonna touch this because I'm afraid that I'm not gonna be able to come back to the presentation. So I'm just gonna make a picture to say what I wanted to show you. That is that when you have a closed curve that is convex, then you're gonna have that the curve is regular until a finite time where the curve shrinks to a point. And then there's a later theorem, not much later, that shows that every curve becomes convex in finite time, so the first theorem applies. And there are lots of videos on YouTube that you can watch this phenomenon. I wanted to show you one. I'm not gonna do it though, because it seems complicated now. So I'm just gonna make a picture. I'm gonna try to make a picture. And for instance, then if you have like a curve like this, that's not what I wanted to do. If you have a curve like this, then the convex points are gonna move towards inside. The concave points are gonna move like this. They're gonna move like that. I'm zooming there, so I'm gonna take out the zoom. And then the curve is gonna start looking more and more convex in time. Eventually it's gonna become something that is convex, and then it's gonna start looking more and more round. And eventually in finite time, and you can compute exactly what the time is. If you look at the previous slide, the time that it takes to shrink to a point. And I think I didn't write it, but the time that you take to shrink to a point is exactly given by the enclosed area. And the reason for that is that you can compute the evolution of the area, and you can compute a precise evolution for the enclosed area, and that gives you exactly when the singular time occurs. And I want to mention that because I'm gonna use that later in the talk. Okay. Okay, so now I'm trying to go finally to the title of my talk and try to explain what is a network flow. And for that, I want to introduce a problem that you can ask, that you can ask even to someone that knows basic geometry. I don't know if someone that knows basic geometry can answer the question, but there is the following. So suppose that you take a circle and you mark 3 points on the circle. And this is one of the most difficult things for me when I'm doing some talks. I don't know exactly if people are following or not, but then if I were like with you in a room, I would ask, what is the minimal connection that you can draw between these 3 points that is completely connected? What is the best way of joining these 3 points that minimizes length? Because remember that the mean curvature flow, when we're talking about curves, is something that minimizes length. That would be equivalent then to minimize area. And now I would wait for someone to tell me what would be the minimizer in this case for these 3 points. But I don't know how to work that out in Zoom. So I'm gonna think that you're thinking
a triangle, no?
You mean something like this?
Yes.
No. Thank you for participating, though. I really appreciate it.
The Mercedes.
Gracias, Alex. I think he has seen this before, but thank you all the same. And then the minimizer in this case is this configuration, where the angles here are all 120 degrees. This is the minimal configuration, and this is something that you can do with calculus. It's not so hard to do, but it's something that one is not very used to think about. And then if you want to think about, for instance, materials are minimizing interfaces and you have 3 states, this is sort of a natural configuration that would appear when you're minimizing energy. So then if you want to minimize energy in a more general context, the class that I was discussing before of regular curves is not good enough. And that's what I mean by the network flow. A network will be something that is composed by curves that are regular, but has some irregular points in between that are what I call the nodes. There are these things in between. So, and then of course, I mean, I'm gonna ask more general things. What if I have, instead of 3 points, 4 points or 5 points or other things? And this is not what I want to do. I want to move on. So I'm gonna define a network, as I said before, as a family of curves that their ends would meet other curves, and that would be like the triple point that I had in my previous picture. Yeah, I went back. So this is what I'm gonna call a node. I'm gonna mark the node in green. And then you have some sort of boundary condition that could be Dirichlet or Neumann or your favorite type of boundary condition. Note, however, that the node in general, when I'm evolving, I'm going to allow the node to move. So it's different than the other boundary condition that somehow has a prescribed way of moving. In some sense, I don't know how the nodes are going to be moving. And well, I'm defining node there. And I'm going to say, as I said before, a network is going to be evolving by mean curvature flow if it's a network for all times. And each of the curves moves by curve shortening flow. That it's a network for all times imposes a boundary condition at the endpoints. That means that the endpoints have to touch. But if you look at this as a PDE, that is, I guess, what most people here are used to hear, you need an extra condition to have the PDE well defined. And that extra condition is something that I mentioned in this particular case before. There are the angles that the tangents form at that point. You need to impose some condition on the derivative at the meeting point to have a well-defined PDE. And the more natural when you're trying to minimize is that the angles are 120 degrees between any two curves. That tells you that you can be meeting all in groups of 3. So for a regular evolution of the network flow, I'm gonna say, I'm not trying to change, yeah, okay. That at every time I'm gonna have only groups of 3 meeting and that they're gonna meet at 120 degrees. So that would be a regular evolution. And then the problem of regular evolutions, at least the short time existence, has been studied in many different contexts. The proofs are often kind of hard to read and they try to, okay, so just a name, that the 120 degrees called the Herring condition. And yeah, so that gives you a PDE. That is the PDE that I'm writing here. I'm gonna translate that PDE into something that is easier to understand in a few minutes. But for now, as you see, I have as before that in the normal direction. And this is kind of not well written. There is an extra thing here, sorry, there's a typo. That last normal there should not be there. I cannot write somehow. That should not be there. So this is exactly the PDE that I had before, that in the normal direction I'm moving like the curvature. And because I rewrote the equation when I was doing this. I had it written in a different form in another presentation. So here you're just thinking that this is ignore the thing before. This is the normal. Ignore the thing that is below. And this is the curvature. The conditions below are the boundary condition. The first one tells you that they meet at their ends. And the last one, the one that says that when you're adding the tangents, that gives you 0. This is exactly the same as asking that the angles are 120 degrees. This is a way of writing the 120 degree condition. Okay, as I said before, a lot of people have studied existence problem. usually when you're talking about, here you're going to have a system of PDEs. Even when you have one, you have a system of PDEs, but you can translate it into one equation by writing things as a perturbation, from a perturbation argument. But in this case, you're not going to be able to get rid of the fact that you have a system of PDEs and that you need to have some sort of compatibility conditions for the system of PDE. And all these existence results that are here deal with different sort of regularity for the initial condition. In all these cases, you have regular curves. I mean, just 120 degrees and curves meeting in 3 as before. But for the first few results, in order to apply the standard theory, you need that the meeting conditions is satisfied to a higher order. That means that in some sense, the meeting condition also satisfies the PDE, that you can take derivatives on the meeting condition and still satisfied for the initial data. And then the later papers, these ones that I mentioned at the end, Mantegazza, Noga, and Tortorelli, and this Magni, Mantegazza, Noga, they try to relax that. They try to find existence when you only really have the 120 degree conditions, so just a one-order derivative, and this is a lot of work. I mean, these papers are each of them like 100 pages. So just to say that actually the existence problem is much more complicated in this case than in the regular case. Okay, so what am I going to talk about now if this is already done? I want to discuss a little bit what are the singularities that the flow can develop when you take a very general initial condition. And I yesterday started trying to draw what I would do today, and I wasn't very successful because I wanted to do one thing that had all these things. So I'm just going to talk about this separately. And then I'm going to say what happens when you try to join all these things. So one thing that you can have are loops in the network. So these are different types of loops, and I drew all of them because they have different behaviors. A similar computation of the one that you do in the regular case, you can do in this case, and you can compute exactly the evolution of the area enclosed by one piece of the network. And then what you find is that, as in the regular case, in this case, the enclosed area, that is gonna converge to 0. So when you try to see the evolution of that, in finite time, you're gonna encounter something that looks like this, but that the angles may not be satisfying the 120 degree conditions anymore, because it depends how this network is shrinking to a point. It's not clear that you're gonna have the 120 degree conditions when this thing shrinks. Even worse, in this case, you also would find that the enclosed area would shrink. But you're gonna find something that is even less regular. You're gonna find something that is like a cross. I mean, the curves are not gonna be straight either, but you're not even satisfying the condition of meeting in 3, so for sure you're not satisfying the 120 degree condition. In the picture below, if you try to do the same computation for area, you're gonna find that the area is not even shrinking, and this is preserving area. This is preserving the area inside. And for the last picture, you're gonna find out that it's even worse, that the area inside is increasing. And here, the area inside is increasing. So if you try to do the picture that I wasn't able to do before, so if you try to put everything in a single domain, let me try again, to put everything in a single domain and join all these things with each other, you're gonna find all types of singularities. You're gonna find that networks, I mean, different loops may be colliding with each other. Some singularities may be degenerating in some parts of the network and in others not. And you can even have, and this is a picture I didn't draw there because I didn't have a boundary, you can even have that some points of the network are colliding into the boundary if you're not careful what the boundary is, if you don't know what your domain is. This may happen, and this may happen even in the example that I drew before of the 3 curves, if you put the 3 points very close together. My picture before was a very perfect Mercedes-Benz type of sign where you had some sort of symmetry there, but if these points are very close together, you're not even gonna have a minimizing configuration. Because, I mean, you're gonna have a minimizing configuration, but it's not gonna be a network. It's gonna be something that looks like this, more like this. So in some sense, the existence result is very nice, but if you want to generalize it for things that are more complicated, surely you're gonna run in finite time into things that are more complicated. So this is the goal of my talk, sort of try to talk about existence when you have initial conditions that are not regular, that when you don't have the 120-degree condition, and when you can have even more than 3 curves meeting at one point. Here, just to explain what I wrote before, in the computation before that I didn't do, when you have loops that are with less than 6 sides, you're gonna find out that the enclosed area decreases. When you have equal to 6 sides, the area is preserved. That was my 3rd picture. And my last picture, it had 7 sides. So in that case, you're gonna see that the area is increasing. It may happen also in finite time that some of the sides are disappearing, and then you're passing from one category to another. This also can happen. You cannot rule out this behavior. So you have all sorts of singularities. So even what I'm gonna talk about now is sort of a very sort of mild situation on how the initial condition can be. I'm not gonna allow, for instance, singularities to accumulate or things like that. Okay, the main theorem is written there. I'm gonna try to do a picture that explains what I'm trying to do here and what I'm really gonna explain. I'm not gonna explain the result in full generality. I don't know even if I'm gonna have time to explain the proof in not so full generality, but I would like to at least explain what we're trying to prove here. And for that, I think it's better to do a picture. Trying to do a picture. So I'm gonna try to draw space-time here. And I'm gonna think that I have a network where many curves are coming out of 0. You have to pose also some sort of boundary condition, as I said before, but what I'm gonna really talk about is how locally you will see the evolution. And then what you expect to see here is somehow that immediately, in instant time, you're gonna have something that is regular. So what you should see for every positive time is something that looks more like this. That is more like a regular network. And then to get a full existence risk, and what the last part of my theorem here said, that the property that the gamma t is gonna converge to the initial condition in a very strong sense, means in terms of the picture of the next picture that I did, the picture here, that I'm gonna try to give a very precise description on how these curves are separating. Certainly you're having a singularity there, but I'm gonna try to do a blow up that gives you a good sense in which the singularity is forming at the initial time, or how you're coming out of the singularity rather, because you're starting with a singular point. And also, I'm gonna tell you how many solutions you have, because the problem will have a non-uniqueness property, or rather than give you how many you have, I'll give you an upper bound on how many can you have. And then to obtain a more general result, what one would need to do, and that we think it follows from our methods, but it's not really written in all detail, is that by taking all these pieces, you can write a solution in a very general case by gluing all the solution. In any case, the solution is based on a gluing technique, so it should be easy to generalize when you have many singular points, provided that they're far enough from each other, that they're not colliding immediately. Okay, but I'm gonna, for simplicity today, describe something with just one singularity, many curves, and see how that evolves. So my initial condition is gonna be like the blue curve below. So I'm thinking something that looks like an initial condition. Sorry, an initial condition that looks like this, in principle, and try to find existence for something that you start with curves like that. And at the we're putting at the domain at the other side of the domain Dirichlet boundary data. You can also do it with Neumann in a similar way, but you need to glue, let's say, what happens at the other end. So a couple of remarks about the proof. This result has been already established in some situations by Tom Illman and Andre Neves and Felix Schulz, and they consider networks with only one node. Their proof cannot be extended for networks with several nodes in general. They cannot allow loops in their networks. We can allow loops for the existence. And the difference of our method with their method is that we're trying to use, or we use something that is called microlocal analysis. The microlocal analysis techniques would usually aim to do is to have a very accurate description of how singular points behave. So that's the kind of method that we're gonna be using here. And until what time do I have, by the way? How much time do I have?
It's 15 minutes.
Yeah, okay, good. So the first thing that I want to do is sort of explain what is, or try to explain what is microlocal analysis. And for that, I'm gonna first introduce something that we're all very used to, that is, think that you have a domain like this, and that you, no, that's not what I wanted to do, and that you write the domain in polar coordinates. So you're thinking about coordinates are theta. So if you write in polar coordinates, you're thinking in the usual coordinates, you have r cosine theta, r sine theta. And that domain, and this domain, if I'm thinking about the domain to be just that quarter, has clearly a corner there at r equals 0. Somehow, microlocal analysis, what would do when you're trying to describe an equation is write it in polar coordinates and understand what is the behavior in theta when you're approaching r equals 0. In the regular coordinates where you're approaching that point, the coordinate system degenerates because you don't see the many directions. And usually the idea of microlocal analysis is try to incorporate this other dimension, the theta direction as well, that would tell you what happens if you approach in different ways to this point. And usually the way they draw this, most people doing microlocal analysis, is that they consider a blow up because in some sense, what you're adding is a quarter of a circle there. In our case, we're dealing with a parabolic problem, with a parabolic equation. So if you try to, we still have something that looks like this, but what would be the y variable, the vertical variable, is something that is the time dependence, while the other one is the space dependence. And somehow, if you try to do polar coordinates, this is not going to behave well with the equation because it doesn't respect the scaling of the equation. So what you need to introduce in a situation like that is what they call a parabolic blow-up. And to try to explain what a parabolic blow-up is, I'm gonna just introduce the heat equation and try to show you things that you're familiar with. I'm thinking about here in a picture as before, so I'm trying to solve a heat equation or a system of heat equations in just the positive direction. I'm prescribing something also on the time behavior at the node at x equals 0. So the second condition, this one, refers to what's happening at the 0 point in time. That is going to be, in our problem, the nodes that we have to allow them to move. And in the space and an initial condition. That is the other one. So the one that I'm gonna mark in green, it represents the initial condition. And in this case, if you want to do something like polar coordinates and respect the equation, the natural coordinates that you need to introduce are things that look like this. It's something that instead of taking x over y, that would be something like tangent theta, that would give you the theta in the regular polar coordinates, you have to take something that is like x over square root of t. The two that you see there in this choice that I have here, it's just cosmetic, because then when you take derivatives of the square root, I want the two to cancel. That's why I put a 2 there, but you can just take it out and take x over square root t, and it should be exactly the same thing. Except that you will have a factor 2 going around in your equation. But these coordinates have one issue, that is that when you go to t equals 0, the coordinate s stops being well defined, and then I cannot see the initial condition. So you have, in order to impose the initial condition, that is something that we know you need for to have a well defined parabolic equation. You also need to couple this with another set of coordinates that is not showing. I don't know what happened. Okay, that also are good at the initial time, but maybe not so good at the other axis. So somehow you will need to interplay between these two types of coordinates and try to see how your equation looks in both coordinates and try to solve that way. Okay, so this is what I'm gonna be talking about when I talk about blown up coordinates. Blown up coordinates are these two sets of coordinates that I'm gonna be using, and I'm gonna be rewriting my equation into these coordinates to solve the equation. What time it is? Okay, so I still have like 10 minutes. And let me go then into my problem. Okay, so a standard thing that you have in parabolic flows when you're trying to understand how the singular behavior occurs is try to do a blow up at that point. That means to do some sort of scaling of the equation at the point and produce a new solution by scaling that has some special behavior. In the case of the network, what you're gonna see if you try to do a blow up at time 0, and I'm gonna be more specific what I mean by this, is expanding self-similar solution. Expanding self-similar solution is a solution of the form square root of t times a fixed curve. So you are gonna see for all times exactly the same shape, just bigger and bigger in time. So that's why it's called expanding, because you have the same shape and it expands in time. There's one more feature that is worth noting in this thing, that is what happens when t goes to 0. And if you see when t goes to 0, if x is positive, what you're gonna see inside the curve is just, inside the argument of the curve is just infinity. So what you're, and because you have something that is going to 0 in front of that, what you're gonna be seeing at the initial time is just the tangent of the curve. So you're gonna see just a line, a straight line, that is the tangent at infinity. While at minus infinity, I'm thinking one dimensional here, you're gonna see the tangent at minus infinity. And that means that expanding self-similar solutions in the regular case, in the regular case, I'm gonna make a picture of this. I have the equation here. This is just plugging in to my original equation, this form of curve. You're gonna get an equation for your gamma 0 curve that is telling you how the curvature should be. And I'm gonna make a picture, and this is what I wanted to do here. So you're gonna have as initial condition something that looks like this, like a V shape, and then for every positive time, you're gonna see something that is regular, that always looks the same, and it's always asymptotic to these two lines. These two lines are gonna be the initial condition, but also are gonna represent, from what I said before, the tangents at infinity of your curve. And when you try to do this with curves, I'm gonna draw the case that I can more or less draw. You're gonna have an initial condition that is gonna be a family of lines. I'm gonna draw just 4 of them. And if you try to find existence for this thing, then the first thing that you notice is that if you go to the picture before, you can have a solution that is just the solution that I had before, tilted, and one on each side. And this is a solution of the equation, but it's of course not a network because I have 2 separated things. I mean, it is some sort of degenerate network if you want. I mean, you don't have nodes. But you can also prove that you have a solution that is of this shape. It's of this shape. I should have chosen a different color here. And that is a network. So you immediately see that you have a non-uniqueness issue here. But you could maybe, if you are very hopeful, that you have only one network maybe. But in this example, it's also easy to see, if you think about it a little bit, that you have complete symmetry. So you're also gonna have a solution that looks like this. So even when talking about self-similar solutions, you're gonna have a non-unique thing coming out of the singularity. So for my original problem, I have no hope of having uniqueness. At most, what I can hope is to be able to classify how many solutions are there and how they look like. And for this is gonna be very important, these self-similar solutions, because these self-similar solutions are gonna classify exactly how many solutions you have of the problem that I was trying to solve before. Okay, in honor of time, since I don't have that much time, I'm gonna just say a few things. I'm gonna give an idea of the proof. And for that, as I said before, the self-similar solutions are gonna play an important role. A result that in the case of 3 curves was proved by Schnurren and Schulze, and in the case for more curves, it was proved by Rafe Maceo and myself, is that if you have a family of n curves or k curves, I think is in the way that is stated here, you always have at least one solution that is a network, and often you have more than one. In a separate result, I showed that in each topological class you have at most one, which means in my previous picture that these are the only 2 solutions, the blue one and the green one. Once you rotate, I mean, once you choose the way they're separating, there's only one way of separating, meaning that I don't have 2 things that look like the blue one. But you may have less. I mean, you have at most one in each topological class, but it's not clear. And in fact, there are cases where you have only solutions in one topological class and not in the other, and this depends on the angles of the curves are forming. In this case, it's very regular. You have that all the angles are the same, but you could also have 4 curves that not all the angles are the same. And in this case, you may have some solutions and others not. And this is something that is not really known yet. Okay, so let me finish in this 4 minutes giving you some ideas of the proof, because so far I haven't proved anything. And the first issue is what I mentioned at the beginning, is that you have a natural degeneracy because you can choose many parameterizations. So the first thing that you have to do to solve your problem is to somehow fix a parameterization with some characteristic. In the regular case, what people usually does is choose a parameterization that only has normal speed component. In the case of networks, this doesn't work because that wouldn't allow the triple point to move. You need to have some sort of tangential velocity, and there's by now some sort of common agreement, or this may change in time, but for now there's some sort of common agreement that the best parameterization that you can choose is something like this. This right-hand side of the equation that I'm gonna mark now is something that has normal part equal to the curvature. So this is something that looks like the curvature times the normal and has tangential speed. And you can compute exactly what it is, but I don't care at the moment what it is. I mean, you have some tangential speed. Plus, this is what each curve is gonna satisfy. Plus, you're gonna ask for the curves to meet at the triple points, and you're gonna have the Steiner condition. At time 0, I'm gonna have all curves meeting at one point, and at positive times, as I said before, I expect this to separate in several nodes, and this is somehow hard to pose, because I mean, somehow you have one domain at time 0 and a different domain at positive times. So a way of dealing with this is to do a blow up not only in the coordinates in which you're computing the equation, but also in the range. And that comes also from the fact of the shape that the self-similar solution had. So the self-similar solution was written like square root of t times something. So if you divide by that square root of t, you're gonna see an actual curve. And if you divide for the self-similars of the network, you're gonna see all the curves that are gonna come out of the node. And when I say in the slide that I had before that I want to blow up the range, this is exactly what I meant. I want to divide by square root of t, and I want to make a description of what happens when you divide by square root of t. And in that sense, we're gonna be attaining the initial condition, because in that way, you're gonna be able to see more or less precisely what happens at the node. And in terms of the blow up picture that I did before, or that I tried to do before, that means that you're gonna have your time variable. Why it's not writing, I don't know. You're gonna have your time variable, you're gonna have your space variables there, and you're adding a whole hemisphere here that you're replacing that point there, but a whole hemisphere where you're gonna see exactly the self-similar solution. And my picture is not very good, and I cannot draw somehow, it doesn't want to write. You're gonna see here in this hemisphere the self-similar solution. Here will be here we'll see the self-similar solution. Self-similar solution. Anyway, I think I'm out of time. So let me just quickly say what the idea of the proof is in just in -1 minute. So the idea is now that you write the solution as that tau, remember that was like it's square root of t. You write this as a power series. You insert this power series into the equation. That's gonna give you a family of equations that you're gonna solve, and then you're gonna try to find your actual solution by a perturbation argument. Let's go quickly, and you're gonna get a family of equations where each equation is gonna depend on the equation before. There's also a remark here at the end that the first equation that you get is the self-similar equation. So there you're choosing a self-similar equation. And when you choose that, everything is gonna be determined by that choice. So somehow you have a freedom of choice that is choosing how you wanna be coming out of the triple point. And after that, you're gonna have a sequence of equations that you're gonna be solving in terms of the ones that you solved before. And that you're gonna see the dog doesn't like the talk. I'm gonna finish now. And then finally you're gonna find the actual solution by a fixed point method by citing the linearization around this approximate solution that I have. And I'm gonna just finish here. If someone wants to talk more about the uniqueness, I can mention it before. Well, thank you very much. I'm sorry for the 2 minutes delay. And that's all that we hope we can have next time that we meet.
Thank you very much, Marielle, for the very nice talk. Questions or comments? I have a curiosity. Could you consider in these network flows non-local operators, like the fractional Laplacian?
Oof, that's a good question. For the regular case, there have been several attempts of the mean curvature flow with fractional mean curvature. I don't know how you pose exactly a problem for networks, because in the regular case, you can try to do the regular thing, or you can try to do what you would call a level set approach. And then you're talking about viscosity solutions. But when you do viscosity solutions for networks, you have immediate flattening. You don't see a network anymore. So you cannot do viscosity solutions for networks. So I'm not sure what would be in the fractional case. How would you pose exactly the condition at the triple point that is a local condition?
Okay, nice.
This is something I wanted to ask you because I didn't understand very well. You do have to put some boundary condition at the nodes.
Yes.
You know? And how do you choose that? You're choosing that.
I'm choosing that they're meeting in 3 and that they have 120-degree angles, because this is the minimizer in the more regular case. So you expect, if you're looking for a minimization, this is the thing that you naturally expect that will happen.
But in the proof, when you make this change of variables.
Okay, yeah, that's a very good question. It's because when you take this power series and you're solving for the power series, some of the coefficients, the matching of the coefficients, and to have what they call the Lopatinsky-Shapiro conditions, you need something of this sort. That is where you're gonna see it.
But somehow you're choosing which curves meet.
Yes, I'm choosing which curves meet. And the way I'm choosing they meet, if you're thinking just about one node, is that they meet exactly like the self-similar solution does. And there's where your choice of self-similar solution comes in as well.
But this choice couldn't give you different solutions.
Once you make the choice of the topology of the thing,
okay,
there's only gonna be one. But you can make many different choices, and this is exactly what I skipped at the end, that you have different choices and you have these different solutions. And you actually do have different solutions. I mean, there is a non-uniqueness.
Okay, thank you.
If there's no more questions, let's thank the Mariel Sáez again. Thank you, Maria.
Thank you.